Okay, so in this video, we're going to talk about subsets and set equality, and this will actually help us nuance a few things that we talked about in the video on sets. So let's start with a definition. We're going to first define what a subset is. And we say that a set S is a subset. It is a subset of a set T, if for all, let me write that again, for all elements X that is in S, we have that X is an element of T as well. X is an element of T. Okay, so a few things to point out here is the quantifier for all. It's not some elements of S. It's not there exists an element of S. It is every single element of S has to be an element of T for S to be a subset of T. Also, the way I'm using the symbol X, the element X here, since it's in front of a quantifier, I'm using it as a dummy variable, okay? What this means is I could use X, I could use Y, I could use Z, any symbol that you want. It's just a symbol that we use to represent every element of our set S. It doesn't mean that you would find X in the list of objects that S is comprised of, okay? So we're going to be using the notation here. It's kind of like a magnet symbol with a line underneath to say that the natural numbers, for instance, is a subset of the set of integers. And we can also say that the set of integers is a subset of the rational numbers. The rational numbers is a subset of the real numbers, and the real numbers is a subset of the complex numbers. Okay, but you cannot say that the set of integers is a subset of the set of natural numbers, okay? So this is not true. And this is because there exists some elements in our set Z, such as the negative numbers, that are not elements of the natural numbers. So our definition of subsets will actually help us define what set equality is. So what does it mean for two sets to be equal? Now, we say that two sets S and T are equal if S is a subset of T and the reverse is also true, that T is a subset of S. Now take a moment to appreciate how this definition right here is very organic. It abides to what we would intuitively think as two sets to be equal. Because if I have two sets, for instance, A and B, that are equal, well, naturally, I would expect that every element of A is an element of B, and every element of B is an element of A. And this definition will help us justify why the multiplicity of objects doesn't matter, and the order as well doesn't matter. If I had a set A again to be 1, 2, 3, and I have another set, let's say B is the set 1, 2, 3, and 3, and this satisfies our definition of set equality. Every element of B is an element of A, and the reverse is also true. Every element of A is an element of B. So this is what allows us to say that those two sets are equal. The same thing goes for the order of the objects. Okay, so let's say this is C. Every element of C is also an element of B and A, and the reverse is also true. So another thing that I should nuance is when I say, for instance, when I said that S should not contain itself, and I said that S is not equal to T. This is true, but I should have been a little bit more precise. We have no issues whatsoever with T being a subset of S. That is okay, okay? But what we take issue with is S being a subset of T, okay? We're not allowed to have S is a subset of T in this situation. Now, one last thing I want to go over is C and then use this magnet symbol again, but I'm going to omit the line that is underneath. So this would mean that C is a proper subset of D. And be very careful, because in some textbooks, they will omit the line underneath the magnet symbol, but they will take it as being a subset, okay? Sometimes they consider a proper subset to be this right here, okay? They put a not equal sign underneath the magnet symbol. I think that is a little too heavy to write, so I'm going to stick with this notation right here. So C is a proper subset of D. And what this means is simply C is a subset of D, and we know that D is not a subset of C. Okay. We can also say that C is not equal to D. So let's go over our definitions one last time. We say that a set S is a subset of a set T if for all elements X that is in S, we have that X is an element of T as well, okay? So this is the notion of inclusion. For our set equality, we say that two sets S and T are equal if S is included in T or is a subset of T and T is a subset of S.